Wait. Okay, I think it's about time. Welcome back to DSP. And let's recap first. So last week we are on the topic of designing an FIR, low-pass filter, finite impulse response, FIR. And the way we do it is to apply a window. So remember that, so here, let's take a look. So remember that we're trying to design a low-pass filter, and ideally you want to have a very sharp transition between passband and stop band, but it's impossible to implement that. So therefore, after we apply a window, we know that in the frequency domain, this ideal response is going to convolve. It's going to convolve with the Fourier transform of the window. And let's say if your window is a rectangular window, maybe its Fourier transform will look like having a main lobe in the middle and several side lobes when we get far away from the middle line. So main lobe, side lobes. So consequently, 导致呢, so when we convolve the two spectrums, we get the result we get is a sort of a low-pass filter, which of course is not ideal anymore. In that it has a transition, a gentle transition, a graceful transition, 优雅的 whatever. Yeah. It has a transition from between passband, still roughly here, and stop band, like beyond the cutoff frequency. So that transition is gradual. It's not ideal. It's not that like that anymore. So. And secondly, so that first thing, we have a smooth transition between passband and stop band. And also in both the passband and the stop band, we have ripples. 就是点一啊, ripples. The gain is not strictly a constant. So there is up and down in the passband, up and down in the stop band. So that's generally what happens when we design an FIR low-pass filter using Windows. Okay, so let's recap. So when we say using window, our design would be something like this. We are going to multiply the ideal impulse response, which is a sinc function. This is for low pass is going to be a sinc function in discrete time, and we multiply that with a window function, time domain multiplication, frequency domain convolution. Okay, so that's where we're at in the past 2 weeks. So what? So we are saying, so let's copy this. So this is an important shape. So in general, when we do the Fourier transform of W and denote the result as, let's say, W of omega, sloppy notation, it's a spectrum. The spectrum generally looks like there is going to be a main lobe of certain width and some side lobes. Main lobes and side lobes, when we get from zero frequency toward, let's say Nyquist is right here, pi equals to Nyquist, right? So generally that's what we have. When we take the Fourier transform of a window, it generally looks like this. So last time we said we had a discussion about how to reduce the ripple, right? We talk about, we asked a crucial question, that is when we increase n. We asked that, right? So we were studying together, what if we just increase the window length? let the window extend far away from in time. Will that help our design? Will that improve the performance? And the answer was yes and no, right? Yes and no. Yes, in the limit, the filter approach is ideal, but if you focus at every single frequency, then the answer is yes. So yes and no. We focus at every single frequency, yes, your performance is going to approach, that filter's performance is going to approach ideal when n approaches infinity. Yes, but no, because of Gibbs phenomenon. Turns out that the maximum error cannot be decreased even when n approaches infinity. The maximum error does not go to 0 even when n approaches infinity. And seemingly there is a conflict, but in fact, mathematically, both are correct. Okay, it seems there is a conflict, 看起来有冲突，看起来有矛盾. It seems there is a contradiction, but actually there is no. So the answer is yes and no. Both are correct. Okay, so and there is some mathematical foundation beyond that. When we have a sequence of functions, continuous function that approaches a discontinuous function in one domain, then that convergence is another kind of convergence. It's called non-uniform convergence, for those of you that are interested. So that being said, in practice, our concern becomes, now, do we have to change another kind of window, right? When we say window, yeah, sure, for a rectangular window, there's main lobe, side lobe. What if we take a different approach? Instead of let n approaches infinity, n is, I think, n equals to 2n, all right? So instead of let the window length extend, can we just simply choose a different window function? That becomes the question, okay? Can we simply choose a different window function? And on this page, we see a few examples. We have the straight line, that's our good old rectangular window. And we have some other types of windows by different names, Bartlett, Blackman, Hahn, Hamming. So different names, so they look differently in time, right? So we have some choices. And the insight that, so last time we took a look at this page, and we are seeing, what we're looking at are the Fourier transform of different windows, okay? The Fourier transform of different windows. But first thing, note that the vertical axis, the magnitude is now in dB scale, So therefore, each notch right here, 这个滴下去的地方叫 notch, notch. Each notch corresponds to 0 crossings. So when we take this to log scale, let's say 20 log of that, of W, absolute value, log 10, of course, that gives us the dB, the same magnitude spectrum in dB. So if you do that, then those notches correspond to the 0 crossings. Okay, so whenever you have 0 crossing, you have a notch in there, and maybe something like that, something like that, something like that. Okay, so that's when we take dB of 20 log 10 of the window, the Fourier transform of the window. Okay, that's what we are looking at right now. See, so just taking dB, right? 0 crossings become minus infinity. Therefore, we see those notches. Any question? Anything wrong here? You guys? Yeah. Right, so we see that. So every 0 corresponds to a notch. Okay, corresponds to a notch. N-O-T-C-H, notch. Okay, that's the word. A notch. Notch. Thank you. We need AI, right? Just transcribe my speech in real time. Right. Anyway, so we were looking at these a comparison of 5 different windows and their Fourier transforms. Right? So somebody noticed that, oh wow, in this window, This is Bartlett, if I remember correctly. In one window, our side lobes seem to be wider. And you're right. And in this window, the side lobe has a roll-off, a decay rate against frequency. I don't know how many dB per octave, but there seems to be a nice organization with the slope right there. Whereas in this window, it's flat. So each of them is different. And in this window, it probably has the widest main lobe. The widest main lobe. But there's another factor that's important is to compare the main lobe to side lobe ratio, or a suppression ratio. Okay, the main lobe to first tallest side lobe. What's the suppression? What's the ratio? Okay, and in general, we care about two factors. One is this ratio, suppression ratio. Main lobe to side lobe suppression ratio in dB. We want it to be large. This is the larger the merrier, the larger the better, okay? But otherwise, we also want this main lobe, or should I say 2 times, this is the actual main lobe, 2 times. The width of this main lobe. We also want this, if I denote it by, I don't know what's the symbol, let's just for the time being denote it as delta omega, okay? We want delta omega, do we want it to be wide or want it to be narrow? We want this to be also be narrow. Narrower the better, okay? The narrower the better, okay? So it turns out that these two becomes design goals, okay? And these two are actually conflicting. For one type, generally speaking, when we increase the suppression ratio, we might need to sacrifice the main lobe. Okay? Generally, if you want this one to be big, this one becomes wider, which is not desirable. There is a conflict between these two goals. Why? So we are going to see, this graph is also very, very important to look at. Okay, so the main lobe width. Now that's the notation, delta omega sub m. Okay. So here, you see that the main lobe width, as I just draw right there, I made a sketch, and this is the main lobe width, right? Turns out that, 正好, it turns out that the main lobe width equals to this distance. There is the ripple, the one last ripple in the passband before it makes the magnitude makes the transition to the stop band. So there's the one last maximum right there, near the edge, okay, and which occurred at a certain frequency. And also there's the first ripple in the passband, okay. So from the most positive magnitude to the most negative magnitude, you see what I'm saying? From here to here, turns out that you can show that. You can show that. 这可以被推导了. You can show that this frequency distance equals to the main lobe. Yeah, so this is not completely obvious to you, so that I want to share with you. This is a nice thing to know, okay? Just when we look at the ripple right here, the ripple right there, the most negative ripple, most positive ripple, this distance, the separation in frequency turns out to exactly equal the main lobe width of the window, whichever window you choose. You can choose rectangular, you can choose Hahn window, Hamming window, Bartlett window, you name it. Any window you choose, you have this very nice relation, okay? Which might not be obvious at first, but let me point you, this is true. Okay, so, so that's it. So that's one thing to pay attention to. And then the second thing I want to point out from this graph is, let me read it. Okay, so main lobe width, the title of this, the caption for this figure, as I put it, is main lobe width, that's the main lobe width, versus transition width, Transition width is a narrower range than the main lobe width. okay? Because the way we define transition is the width when the magnitude makes its transition from 1 minus delta to delta, okay? So this width, whereas this main lobe width, you can show that equals to 1 plus delta equals to the width where we made the transition from 1 plus delta to minus delta. So therefore, naturally, please pay attention that the main lobe width equal to that, okay? But the transition width as we define is the width from here to here, from these two corners. So naturally, the transition width is slightly shorter than the main lobe width of the window. Okay? The transition width of your design is slightly smaller than the main lobe width of the window that you choose. So please pay attention to that. Yeah, there's no secret. Everything is just sketched right here. It's shown, illustrated on this figure. Okay? Can you see that the main lobe width is slightly wider than the transition width as it is defined. 按照定义, as it is defined by definition. Taking a look at this figure, you should realize that there's a relation. Okay, but generally you can see that that's why we prefer a main lobe that is as narrow as possible. Because whenever the main lobe is narrow, we can guarantee a sharper transition, a faster transition between pass band and stop band. Okay? Therefore, on one hand, we want the main lobe width to be narrow. On one hand, 在一方面是这样. On the other hand, we want the main lobe to side lobe ratio. When you think about the area enclosed by the main lobe versus the area enclosed by the first side lobe. We want that to be, we want the first side lobe to be small, okay? We also want the first side lobe to be small. And that has something to do with what exactly is delta, okay? What exactly is delta? So let me just point to you the conclusion. Note that, my conclusion is, note that 1 plus 2 delta, okay? 1 plus 2 delta equals to the main lobe area, and the total area equals to 1. The total area equals to 1. By that, I mean when we integrate from minus pi to pi, w omega d omega. The total area, or should there be, I think there should be a normalization factor, okay? The total area, it turns out that for all the windows that we see, the total area is 1. The total area is 1. And there's a reason. There's a reason because 1 over 2 pi minus pi to pi w omega, this e j omega 0, yeah, d omega equals to w of 0. That's a reason. That's a reason. Okay, the total area of the main lobe, the total area of the entire window transform, the Fourier transform is 1, subject to a normalization of 1 or 2 pi. Yeah, and whereas the main lobe, the area underneath the main lobe equals to 1 plus 2 delta. So why do I point out these tiny details? So let's take a look. This area turns out equals to 1 plus 2 delta. You can show that. And whereas when we take, when we consider all the side lobes, negative or positive, okay? Negative go negative, positive go positive, and so on. So when we finally integrate from minus pi to pi, all the area with alternating signs, you know that when we do an integral, negative part, you need to make it negative, right? So when we take the integral from minus pi to pi, the total area equals to 1. So that is to say, that's here. Yeah. That's the total area. Total area equals to 1, but the main lobe area is more positive than the total area. You see that? The main lobe area is 1 plus 2 delta. So what's the conclusion? What's the conclusion? Therefore, we have two areas. This is the main lobe area, and this is the total integration, okay? The entire integration. Integration from minus pi to pi. But if we integrate from minus delta omega main lobe to plus, that is what I'm saying. If we integrate from minus half of the main lobe width to plus half of the main lobe width, if we do the same integral, that's what I'm saying. 1 plus 2 delta. The main lobe area equals to 1 plus 2 delta. So therefore, when we combine the two facts, therefore, 1 and when we consider both of them, therefore, I say therefore is a serious word. Therefore, delta equals to what? Okay? Delta equals to the integral from here to pi. Okay? Yeah. That's the kind of the conclusion I want to point out. Okay? Delta has something to do with this integral. Actually, this is identity up to, I think, still we need 1 over 2 pi. Okay? Not very that important. Yeah. But take a look. This integral is from here to there, right? This chair is in my way. From here to here, the first lobe we get, the first side lobe we get is a negative, right? Negative 1, followed by a positive 1, smaller, and followed by a negative lobe, even smaller. So they alternate the sign, and it's getting each one getting smaller. Therefore, the entire integral from here to pi is in negative or positive. If we integrate from here all the way, blah, blah, to pi, is this integral going to be negative or positive? It's negative, right? It's negative, and the value its absolute value is delta. Because 1 plus that equals to 1 plus 2 delta. That's as simple as that. Is it going too fast? This is a funny thing. This area is, no, the entire area is 1 plus, no, entire area is 1. And this is 1 plus 2 delta, okay? Therefore, here is minus delta, and here is minus delta in terms of the area, okay? So 1 plus 2 delta plus minus delta equals to 1. That's what I'm pointing out right now. I know it's very detailed. It's pretty, 怎么讲？蛮琐碎的. It's quite 琐碎. How do you say 琐碎 in English? Tedious. It's very tedious, but I do want to point out. It's really tedious, but pay attention. 1 plus 2 delta, the main lobe area, minus delta, all the area added up equals to minus delta. And we know it's negative. Okay? Because symmetry here, same thing, minus delta. So when we add all three terms up, 1 plus 2 delta added by minus delta, added by minus delta, the total area is 1. Okay? So that's a relation between the main lobe, side lobe, and the relation. That's a relation. Okay? Where delta is what? Delta is the maximum ripple. Okay? So now the question becomes, how do we suppress that ripple? So now we are finally ready to answer this question. On one hand, we want the design. On one hand, we want the transition to be sharp, and we know how to do it. We want the transition to be sharp, we need the main lobe to be narrow. Okay? First design goal, we want the transition width to be sharp. Then clearly we want this main lobe to be narrow. Okay? That's one design goal. But the second design goal, we want the ripple to be small. We want delta to be small. So what do we control? When we want delta to be small, what is delta? I've shown you that delta equals to that, right? Exactly, there's no secret. Delta equals to this integral. So the way we make this integral small is we want this side lobe to begin with a small value, right? If the side lobe area is small, then this guarantees that delta is upper bounded by a small value. Okay, so yeah, so that's why we want this area, or generally, roughly speaking, we want this side lobe, the height of the side lobe, we want this suppression ratio to be large. Okay, we want this side lobe when you compare to the main lobe, we want this compared to that. This comparison, when we do that comparison, you want this side lobe to be small. Okay? So that's our conclusion. So that gives us some hint as to how do we choose a window. Okay? When we choose a window, we want the Fourier transform to have a narrow main lobe as well as short side lobe. That clear? Okay, that's the conclusion. When we choose a window, you have two goals. You look at the width of the main lobe, and you look at the height of the side lobe. You want the side lobe to be short, and you want also want the main lobe to be narrow. And it turns out that these two goals they conflict each other. Okay? So you get it? Main lobe to be narrow or short, narrow wide. Main lobe to be narrow, side lobe to be short. Okay, so those two goals turns out to conflict each other. 它是有冲突的啊。They conflict each other in this way. So in this way. So let's take a summary. This table is good to refer to. Yeah. So this table shows us a few columns, and the first column we're looking at different types of windows. Okay, different types of window, and you see side lobe amplitude relative to the main lobe. Okay. Minus 13 dB for rectangular. So that means that if the main lobe height is 1, the first side lobe is 13 dB down there. Okay? And that turns out to be the tallest side lobe among all the windows. Rectangular window has the tallest side lobe at minus 13, followed by Bartlett, almost 2 times better. Hung window, even better. This one, even better. The one, the best. Okay. This one has the shortest side lobe among all the choices, which is good. And we've seen that when the height of the side lobe is small, that causes the integral to also be small. Okay, that also reduces that integral. So therefore, peak approximation. Now we are talking about delta. Okay, now we're talking about delta. So roughly speaking, you see that when we have a tall side lobe right here, we have large approximation error. So now when we suppress the side lobe, this approximation error gets better. Okay? When we further suppress the side lobe, the approximation error gets even better and better and better. So these two columns are highly correlated. You see that? In exactly the same order. Okay, they line up in the exactly same order. When we suppress the side lobe height, we improve the peak approximation error. Okay, So this is one thing to pay attention to. These two columns highly correlate each other. That clear? And there's a reason behind that. Behind the high correlation between these two columns. Okay? Yeah, so in terms of the side lobe suppression ratio or the peak, or consequently the peak approximation error, we want to choose the last one. This last one has very nice suppression, and the approximation error delta is just minus 74 dB down from ideal. That's almost perfect. You think about minus 74 dB, that's a very small quantity. That means that when we design a window, when we design a filter, that means this. That means that this ripple there is really small. That means the passband gain is almost a constant. If delta is so small, if delta is minus 74 dB, that's very, very small. Or delta is right here, right? If that delta is minus 74 dB, that's very small. That's less than 0.001. You can guarantee to have a stop band that at least that rejects your signal by 74 dB at least. Okay, that's how good it is. That's how good it is. The passband, the stop band gain is less than minus 74 dB. That's a lot of attenuation. Okay, so if you really want to pursue that, you want to really control the stop band gain to be as small as possible. Choose that last window when you design the FIR. Choose that. Choose the name is Blackman. Choose Blackman window if you really want to pursue this. Okay, but the drawback. The drawback is that unfortunately it also has the widest main lobe in its Fourier transform. The main lobe is roughly 3 times larger than the rectangular window. So what's the implication? When we have a wide side lobe, when we have a wide side lobe right here, when the side lobe width is 3 times larger, 3 times wider, with very small side lobe, okay, almost zero side lobe. This is like what Blackman looks like. This is what Blackman Windows transform looks like versus we compare it with, let's say, rectangular. Okay. A wider main lobe has a consequence that its transition is also going to be wider. It occupies a larger bandwidth to make the transition from passband to stop band. That transition is also becoming wider. Okay, so there's really that's what I mean, a conflict between two goals. We want the transition width to be small. We also want this approximation error also be small. But the two of them, you see an increase of main lobe width from here to here. When you pursue the approximation error, when you pursue to lower the approximation error, you may need to compromise the main lobe width, which directly affect the transition width. Okay, which directly affect the transition width. Yeah. All right. So that's a table you can refer to. If I ever test you on the exam, I will give you the same table. I promise. So this table should be given to you because it's important. It contains a lot of information. Okay. Any question here on this table? Any question? The two columns I haven't mentioned. Okay. So we talk about the peak side lobe amplitude, the height of the side lobe, and we talk about how it relates to how it controls the peak approximation error. Okay? And we talk about the main lobe width, which controls the transition width, but we haven't talked about is a buzzword. What do we mean Kaiser window beta? Okay, this is our next topic. Okay, so we'll stay tuned. We will briefly talk about Kaiser windows when we move on to the next lecture. Right. So anyway, so this is a very nice table to be aware of. Please pay attention to this table. Okay. So I think that's about it. That's about the last page I want to show on this lecture. So maybe we do have some time. I want to invite 3 of you. So we look at the TAs, and the TAs looked at all your homework number 3, and they have been graded. And so they selected a few best reports to me, and then I recommended 3 reports. So the TAs are not here. So we have 3 reports I want to share with you. So, first one is this one, okay? Samuchin, are you here? Is Samuchin here? Yeah. Do you mind to come and talk about your report? So let me say the reason I recommend this report. First of all, it's very nicely written with all the math, and so that's why I recommend this report. It follows like IEEE template. Not that you need to always do this, but this is quite professional. Okay, please consider. Mush is not the only one. You're not the only one using this kind of template. So thank you for doing this. This is quite some extra work with introduction and also and discussion and audio test. Okay. Remember, please recall the audio in this homework. I asked you to process my speech, right? What's the content of that speech? S, F, S, S, F, S. That's homework we were talking about. Now, I asked you to low pass my speech and to see if you can still tell the difference between S and F when we low pass, when we perform low pass filtering. Okay, yeah. We're using IIR because last time we were on homework number 3, we were on IIR. So there's some very nicely composed math. Apparently you know how to do. Well, this is Windows, right? Word file. That's okay. Another option is to use LaTeX. But what else? So there is a conclusion in this lab. We verify the design implementation of this follower filter. The result confirms blah blah blah. And through perceptual testing, we identify frequency threshold where over-filtering renders constant S and F indistinguishable. That's beautifully written. Okay, that's beautifully written. At my age, I wouldn't be able to come up with this beautiful sentence when I was your age. But now you guys have AI, I know that. So it's great. Yeah, it's great to use whatever tool you have to improve your polish your writing. So I appreciate that. And this is probably not so necessary, though. Citing references, that's that's a bit of overdoing. Come on, this is just a class report. But well, I thought this is great. I mean, apparently Muchin put a lot of effort in putting together this report. So let's give a round of applause to Muchin. Yeah, very good. Good stuff. Yeah. Okay, I'll close that. And then the next one is our good old friend Loi Ting, who created like an interface. Who earlier shared with us an interface of AI written MATLAB script. Yeah. So this time, do you mind to come up and tell us about share with the rest of the? 我讲就好了. Okay. I like, as I mentioned, this is LaTeX, right? So you've handled this important skill, that's great. It even has some highly mathematical discussion, like something like that, okay, even with that. Very nice style. I mean, this is elegant style right here with all the tables, yeah. It's almost like this can be a textbook of some sort. So I guess this is really nice choice of font, 中文的字体. I mean, everything is just really nicely prepared. And there's a 听测实验. This is in Chinese, but 听测实验, and there's also the optional part. Also the optional part. You've implemented this difference equation and compared the result with the MATLAB given function, and then you have verified the result using Python, and just very nice, just very nicely presented. I mean, the presentation is good. The look and feel, the kind of infographics, 它的整个呈现是蛮好的啊。So, that's why I choose to share with you Lo Yiting's work. Let's also give a round of applause to Lo Yiting. And the next one I chose is this one. 许书涵啊，许书涵在吗？哪位？啊，许书涵，好。So why do I choose your work? I choose this report. Maybe Shu Han is not the only one who points out this, but this is about processing speech, right? So she did some extra work to really talk about phonetics, 语音学了, for phonetics. What exactly is happening when we say S versus when you say F? When we say S, we're going to expose your mouth. You're going to expose the gum part, the flesh part that's around the teeth, and which causes the breath, the sound of breath, the energy to move toward high frequency. Right? When we say F, F is what we call labial-dental consonant. Now that's a labial-dental 唇齿音啊。When we say F or V, f and V, your teeth is touching your lip, right? Your upper teeth is touching your lower lip, right? So when the teeth as a labial refers to lips. When and dental, of course, refers to the teeth, right? Labial dental, that refers to the condition when we constrict the flow of your voice by making your teeth to touch your lip. Okay? 唇齿音, so that's correct, and which causes the energy to more uniformly distribute. So I think this is a very nice discussion and how by referring to phonetics. Okay, so that's why I want to share Shu Han's report to everybody. So interdisciplinary study, right? This is an opportunity when we use what we learned in the low-pass filter to process speech. What is speech? Speech is produced by your vocal articulators. Go into the 气管, it's produced by your mouth, right? So the anatomy of your mouth matters. 人类的嘴巴的那个结构的解剖, the anatomy of the mouth, the vocal tract matters when we study speech processing. So that's great. So let's also give a round of applause to Xu Suhan. And by the way, labial dental, I have a small something 对人生没有帮助. If you know this, it doesn't help your life. Normally, we produce the F sound by touching the upper row of teeth to the lower lip, right? What if you do the opposite? You will look like retarded. 你看起来像智障，是？Try that. Father, mother. There must be a reason why we don't do that. There must be a reason because I don't know. Think about it when you go home. All right. So that's all I want to talk. So you still have 2 more homework to write. So keep in mind that you can ask each other how to prepare a report. Not necessarily for your best grade, but also, I mean, for self-satisfaction. Maybe 5 years later, when you're in the India, right, you find the report, you want to be happy or you want to put a smile on your face, right? So 5 years later, when you look at your old report, sometimes I still do that. Look at my old paper, my old achievement. Do I have a smile on my face? Okay, so think about that. All right, so that's about the homework. Okay, so you still have 2 more homeworks, and so yeah. Comment, questions? Uh, yeah. So I think we have another midterm coming up, unfortunately, like in 2 weeks. Is that right? I think in 2 weeks. Okay, in 2 weeks. And I think our midterm will cover to whatever the end of today's lecture. Okay. So let's remind each other. Remind myself to the midterm TAs. The midterm will cover till the from where we were left last time in the first midterm to the end of today's lecture. Okay. So with that, in 2 weeks, that's 2 weeks later, and we want to now move on to the next topic, as I promised. The next topic is still FIR. Okay. But in this next lecture, we are going to briefly mention another kind of windows. And they form a family. Sometimes we say the Kaiser family of windows, okay, which is parameterized by beta. Okay? There's a parameter beta that controls the main lobe width as well as the side lobe suppression ratio. So we cover that. The Kaiser family of windows. And then we switch to the another topic that is fundamentally different. Okay? In the next approach, we'll be looking at a formulation. We will formulate filter design as a kind of optimization problem. And we call this approach the optimal approach. For what? For FIR filter design. And there's the buzzword type 1. Okay, type 1. Okay, so first, we are going to explain that you'll discover that the windows that we look at so far, we have Blackman, the Hahn window, Hamming window. The 3 of them actually form the cosine family. Okay. So let's take a look first. This is sort of like a summary. So maybe time for me to erase my board. Take a look first. So when we say we design by window using a multiplication in the time domain, just for the convenience of discussion, we've been assuming that in time domain, the window as well as the ideal function, both of them are evenly symmetric around time 0. Okay, just for this convenience of discussion. We're assuming that our desired response looks like that, a sinc function. If the desired low-pass response looks like that, and when we multiply it with a window, both the window and the desired function, let's say this is a Hahn mean window, for example, this is W of n, okay? Just for the convenience, for the convenience of discussion, both the window as well as the ideal response, both of them are evenly symmetric around time 0. Okay? And there's a reason why this gives us some convenience. 方便是有原因的. Do you remember that? The reason why we find this convenient is because now, when we take the Fourier transform, the spectrum as well as the ideal response, both of them are real, because of the symmetry. And that's why it's easier to discuss the convolution and stuff like that. Main lobe, side lobes. So that's for the convenience of discussion. But in practice, we very soon will know that this window has a time range of -n to n, right? Strictly speaking, what's the problem? Strictly speaking, this is non-causal. Okay? Strictly speaking, this is non-causal. Okay? So you cannot run this in real time. You can run this by post-processing, that's okay. But when we want to implement a system that runs in real time, this is forbidden. This is impossible to do this. Okay. So therefore, in practice, we need to, what do? We simply make a shift. Okay. We simply shift the ideal response as well as the window. Everything we shift it to the right by n samples to resolve this issue. Okay. So in practice, we want to redefine, or the other way to put it is redefine your time axis so that now time 0 is on the far left. This is time 0 of our new time variable. Okay. Just shift everything to the right, and you're going to be fine. Right. So now the window has a length, has a range, a duration that lasts from time 0 to time 2n after shifting. Okay, after shifting, and that's why when we now look at the ideal response, it becomes this expression. Still sync, but the time index is shifted to the right by n samples to make everything causal. Okay. All right. So with that in mind, now our window is going to be defined over the time from 0 to 2n. And I want to point out this. I'll point this out before we take a break. Look, rectangular window, of course, W is all 1 inside that range. But the Hahn window, both the three of them, they actually have closed form expressions. Okay, this is something to be aware of. Okay, to be aware of, we have Hahn window, Hammond window. Both can be expressed in terms of a constant subtract 0.5 cosine something. Hammond window and Hahn window both like that. Different coefficients only, But Blackman window has one extra term. It has one more term, constant first cosine, second cosine. Okay, but otherwise there's no secret. All these windows have closed form expressions in terms of cosine. Okay, so that's why sometimes I call them the cosine family of windows versus our topic next. The next topic is the other family, the Kaiser family. Okay, so let's take a break, and when we return, we'll look at the Kaiser family of windows. 10 minutes break. Oh. Okay, so, all right, so shall we continue? Um, I decided that the midterm will just cover through Kaiser family of windows. We might have some time to go further to the optimal approach, but we'll leave it for the final exam, okay? So the midterm will cover till the end of Kaiser family of windows. I will confirm, please confirm with TA, okay? TA 也请注意，我们就考到 Kaiser 这边啊。All right. So here we have shifted the sync function to the right as well as the window function. This has also been shifted to the right. Okay. So as a result, consequently, our design will still have the symmetry. The final design is just the same thing, but now we define time zero to be the beginning point. Okay. So this is gonna so your h of n now. So let's call the result, maybe we can denote, yeah, anyway. So after shifting, so we say this is H sim. Your result, nothing. We need to give it a different name. So before shifting, let's call the design H before, okay? Yeah, before shifting. Yeah. But now, h n equals to h before, shifted to the right by n samples. Now h becomes causal. You can store all the coefficients in an array and start processing your signal using convolution. Okay, low pass filtering. But now I also want to share with you that the result of a design satisfies type 1 criterion. Okay, type 1. What is type 1? Type 1 definition is down here. When your impulse response has a symmetry such that there is an integer m, such that h of m minus n equals to hn for all n, where n being an even number. So here, note that we have h of 2n minus n, 2 big N minus n, equals to hn for all n. All right? Because the result of your, after shifting, now the symmetry point is time n. Okay? So 2n, your filter is going to have this symmetry, where there is an integer 2m equals to 2n. So the result of the design satisfies what they call, it satisfies type 1 definition. Type 1 definition. Yeah. So for those who are interested, please refer to the textbook. Okay. In textbook, it has a more thorough discussion of type 1 versus there is type 2, okay? And type 3 and type 4. 4 different types, each having a different symmetry. But type 1 is when m equals to an even integer and we have this even symmetry, then the result is called a type 1 system or type 1 filter. Okay, so we've looked at this. Now, still, take a review of this table. There are 2 more columns that we haven't discussed. Turns out that when you look at the approximation error right here, you can find the corresponding parameter for Kaiser family window, and this is what we're going to talk about next. Okay, so for the Kaiser family of windows, you can directly control the approximation error, the largest approximation error, continuously. Okay, so beta now is a real number. Okay, so and this family of windows we're going to look at is parameterized by one continuous parameter beta. Okay, so by choosing beta equals to 0, you get this approximation error. And by choosing a larger beta, you get a better approximation error. And then there's the same trade-off between approximation error versus transition width. Okay, when we suppress the approximation error, inevitably we increase the transition width. Okay, so that's the design philosophy that we need to introduce to you. Okay, so now let me just read this. So there's another family of windows that can be constructed, and they will outperform the cosine family for FIR design. So the take-home message is that you can do better. Okay, you can do better than last week. Okay, than homework number 4 by knowing the Kaiser family of windows. Okay, they generally outperform, and that's a take-home message. The kind of filter you design generally outperform cosine family design in terms of the trade-off between approximation error and the transition width. They generally outperform. The reason will be clearer in a moment. And let me also point to you that the Kaiser windows is continuously tuned by a parameter beta, a non-negative parameter beta. And so that's kind of the advantage of knowing Kaiser family window. But of course, cosine family has some other advantages, which I'm not going to talk about today. So yes, for interest, cosine family of windows also have their advantages. But we'll see if we can cover it near the end of the semester. So don't worry about it for now. Okay, but let's focus on Kaiser family of windows. The Kaiser family of windows will be our next topic. So now take a look. W, the window function, is now, this W is defined by that over that. Okay, thank you, class dismiss. That's a definition where, let's take a look. Where this I function, I0 function denotes the 0th order modified Bessel function for the first kind. Okay, so repeat after me. 0th order modified Bessel function of the first kind. 0th order modified Bessel function of the first kind. Okay. I'm sorry. Okay, Bessel function shows up for no reason. Now, what is Bessel function? Bessel function, 0th order modified Bessel function of the first kind. Okay, has a Tyler expansion, power series expansion for your information. Okay, it's a branch of math which somehow shows up here. But then, yeah, I mean, just generally speaking, this I naught beta is just a normalization factor to make Wn equals to 1 in the middle. Okay, so that's just a normalization factor. But now we need to, is that clear, right? When you plug in n equals to small n, then the top becomes I0 of beta square root 1 minus nothing, right? So this is just nothing but a normalization factor. That clear? So don't worry about that. This part is just a normalization factor to make the value equals to 1 in the middle. Okay? Make W equals to 1 in the middle. But now, if you take a look, now beta, what does it control? It controls the width, the shape. Right? Generally, when we increase beta, you expect the width to become narrower in the time domain. Okay? And so I hope I have a plot somewhere. This is it here? Yeah, so take a look. It's a bit small, but bear with me. So here is an example of 3 different beta values. It might be easier if you refer to your iPad, okay? But let me read it. We have beta equal to 0, beta equal to 3, beta equals to 6. Okay, maybe I need to elaborate using the board. So here, let me copy the panel. We have beta equals to 0, and the duration is from 0. Let's say in this example, the duration is from 0 maybe to 20, okay? So yeah, 0 to 20, 21 samples in total in time domain, a causal function. So here, this is beta equals to 0. Actually, beta equals to 0 is the rectangular window, okay? So beta, when beta is 0, this Kaiser equals to rectangular. That's the first thing to be aware of. But as we increase beta, this bell-shaped function is becoming narrower, right? Generally, it looks like bell-shaped function, beta equals to 3, might look like something like that. In the middle, when n equals to 10, it approaches 1, okay? Maybe like that. Of course, this needs to be symmetric. And when we further increase beta, it looks like that, okay? When we increase beta. Is that clear? In the time domain, that's what's happening. When we control, we can continuously control the width of your window function using any beta. Okay, beta does not necessarily need to be integers. 不见得是整数啊。Beta is not necessarily an integer, but you can continuously control beta to change the shape of the window function in the time domain. Okay? So therefore, when we take the Fourier transform, why do we want to study the Fourier transform window? Because we want to look at 2 things, right? We want to look at how wide the main lobe is, and we want to see if the side lobe becomes short. 2 purposes, right? So let's take a look. Again, when we compare beta of 0, 3.0, or 6.0, 3 different cases. So this is a busy plot. Let me actually enlarge this, okay? I think I will be able to enlarge this slide by this. Can I enlarge it? Okay, let's do this. All right, so now we have a closer look, right? 3 beta values. What do we have? First of all, do we want to look at the main lobe width first or the side lobe height first? Main lobe width, maybe we look at the main lobe, right? So the main lobe, you see that when beta is 0, it has the narrowest main lobe width right here. That's beta when we look at the first notch, right? Notch is a 0 crossing, right? So that's the main lobe. And whereas when we increase beta, what happens? When we increase beta, the main lobe width also increases, which makes the transition slower, okay? The transition width is going to occupy a wider bandwidth right there. It takes up a larger space to make the transition from passband to stop band, okay? That's the implication when we see an increase of the main lobe width, okay? But meanwhile, that comes with an advantage of better suppression of the side lobe, okay? So now, beta equals to 0 has a relatively high side lobe. We already know that it's minus 13, rectangular window. Has a 13 dB main lobe to side lobe suppression. Whereas when we increase beta, now the suppression improves to something like minus 20 something, okay? 负20几了, improves. And we can further improve it by further increasing beta. So when we go to beta equal to 6, now which one? We're looking at this one. Is it? No. This is quite busy. This one right here. Yeah, that's beta equals to 6. Now the suppression, now the side lobe ratio further improves to lower than minus 40. Before this is ideal, it improved all the way there. So improvement further improvement. But that comes with a compromise. Narrow is side lobe, narrow is main lobe, now a bit wider main lobe, even wider main lobes. So you see the conflict of our design goals. There is a trade-off. There is a trade-off between these two factors. Okay, is that clear? There is a trade-off when we compare the three cases, okay? Really, this is not that hard. So taking a look at this figure, you can understand there is a trade-off. Okay, so keep in mind there's a trade-off. Then, what if we plot? What if we study the two factors? Okay, so we also know that the main lobe width has something to do with the transition width, right? They highly correlate. So if we plot, let's say, if we plot the transition width versus the peak approximation error, 20 log 10 of delta. Remember that delta correlates to the height of the side lobe. Okay, there is a high correlation. This correlates to the side lobe height. Whereas this reason correlate. Okay, this is a sort of a sloppy notation. Delta correlates to the side lobe height, whereas a transition width correlates to the main lobe width, or is affected by the main lobe width, is controlled by the main lobe width. Okay, so now, if we somehow change the beta continuously, what do we expect to see? Do we expect to see a trajectory of performance? Okay, so from here, for example, if beta, when you increase beta, we expect the transition width to widen. Okay, whereas the suppression ratio to the approximation error to become better, right? More negative. Okay, so we should expect some kind of a inverse relation right here. So that's a trade-off. You expect to see a trade-off line right, like that. That shows when we increase beta. Okay. When we increase beta and we plot the performance in a two-dimensional space. If you plot main lobe width, if you plot transition width, versus peak approximation error. You should expect to see an inverse relation, where the peak approximation error improves with the cost of increasing the transition width. Okay, so there should be a trade-off that can be generally expected. 大致上可以有这样的预期啊 which show the trade-off when we increase beta, and you get the idea. When we increase beta, indeed the main lobe increases, whereas the side lobe decreases. So there is a trade-off, and you probably can expect a performance curve like that. So guess what? You refer to the note. This is generally right. And miraculously, I don't know why, it looks almost like a straight line. This is miracle. Okay, so miraculously, this is almost a straight line. After studying DSP for 30 years, I don't know exactly what's the reason. But miraculously, the insight is beautifully, it's right, it's correct. You see approximation error as defined right there, 20 log 10 delta. Gets better and better when we increase beta. So this is Kaiser 1.0, Kaiser 2.0, Kaiser 3, 4, 5, 6. In between, we have fractional numbers. It's all right. But when we line all the dots, they almost form a straight line. Almost, not exactly, but almost. And by the way, let me mention, this is a figure from the textbook, and there are some design parameters. We are restricted to the case of m equals to 32. Okay, when we have 33 samples for design, m equals to 32 type 1 filter with a color frequency right at half Nyquist. This is one example directly from the textbook. Okay, you see that it's almost a straight line. Okay. Increasing beta improve approximation error. You have a better control of approximation error, and with the sacrifice of having a wider transition width. Okay, inevitably, 无可避免的. And this is a trade-off for our Kaiser family of windows. Yeah. Whereas now we see all four separate dots, right? Four separate dots of the performance. Blackman, Hamming, Hanning, and Bartlett. Okay, so see that all the four dots are on this side of our straight line, right? So now can we conclude which one is better? Is the Kaiser family of window, do they give us a better design, or does the cosine family give us a better design? Now you can answer that. Which family is better? Which family is better? All the cosine results lie on this side of the straight line. Okay? That shows that the cosine family is outperformed. Okay? 被胜过了, 被完胜, is outperformed. Is that clear? Because if you compare, for example, this Kaiser, somewhere here, this Kaiser 4.3 has a narrower transition width than Hanning, as well as a better approximation error than it. Okay, so therefore, this family, among this family, you can find a window that outperforms the Han window in terms of both the approximation error and the transition width. Therefore, this straight line outperformed all the four dots that lies on the upper right half of the plane. Cosine family is outperformed by Kaiser. Okay, so that's something I want to share with you. And let me also read this. So now, sort of to summarize what we have learned so far. So now, in terms of design, okay, in terms of design, just like homework number 4 and 3, you might be given a tolerance level, okay? So when we think the opposite, when you're designing a filter, you are given a tolerance level. So now from there, you can then first choose a beta, okay? So let's say your spec tells you that the tolerance is minus 60 dB, the pass band, the stop band gain should be smaller than minus 60 dB. Fine. We'll just choose a Kaiser. So it seems that the beta value should be in between 5 and 6. That's the way we do the design, okay? First, study the approximation error specification, and then just put a beta value somewhere. And now you can expect the transition width, okay? If m is 32, if m is 32. All right, so let me complete reading this summary right here. To design, first you might be given a tolerance level, or you can, or in some cases you can select a tolerance level. Okay, so from there you can then find the beta, and then finally, you know, if we have this beta, the transition width is going to be right here when m is 32. Now, if you need a narrower transition, what do? Then that's the moment when we can finally increase m to satisfy the transition width requirement. Okay, is that clear? So, the design process is to first look at the desired, how much you want to control the error, and then choose a beta, and from there you can then adjust m to also satisfy any transition width requirement. Okay? So we might need to go back one slide. This is might not be exactly clear, but if we go back one slide, I remember here. Here we have the case of same beta, but different m. Okay? Same beta, different m. Let me also enlarge this plot. So you see that this is an example of keeping the same beta. Okay? I forgot, this must be beta equal to 6, okay? When beta equal to 6, naturally, you can adjust m. By making it longer, then you will be able to make the main lobe narrower, okay? Going from right to left, okay? And we know that main lobe width controls transition width. So that's sort of the general idea how you design a filter, a low-pass filter using the Kaiser family of windows. So that's it. That's it for this midterm. Okay, this upcoming midterm, 2 weeks from now, you'll be tested all the way till this slide. Okay, and next week we have some time for review. Okay, so I'll come up with some activities next week. Next week will be no lecture, but only review and homework. Okay, there's still a homework to come, but I think it might be good that we don't have any extra lecture next week. Right? 这样可以吗？下礼拜四我就先不讲课，我们可能利用礼拜三时间做一些 review。We'll use next Wednesday for review. Okay, so yeah. So anyway, so this Kaiser function surprised me when I first encountered it. I was seeing a beta function, I was wondering what's going on. Bessel function, parameterized by beta. But anyway, it's not like in practice you refer to this figure. Okay? In the textbook, there are actually some empirical formulas. In the textbook, you'll see some empirical formulas as to how we choose beta according to the desired approximation error. There's an empirical, 就是经验公式, empirical formula. So if you're super interested in the textbook, there are some empirical formulas. For the choice of Kaiser window, as well as the choice of window length, m. As well as for choosing, for what? For choosing beta and m. Okay? But I prefer not covering it. If you are very interested, please refer to a textbook. Okay. All right. So let's take a 2-minute break. 休息2分钟. Let's take a 2-minute break before switching to our next topic. Okay. Yeah. Okay, I guess we covered a lot of materials today. So for the next maybe 10 minutes, I want to just give you some sneak preview. 我就稍微预习一下，当做是预习啊。I'll give you some preview of our next topic of FIR design. And this time we are going to formulate the problem as an optimization problem. Optimization 最佳化啊。So you will come back to this after the midterm, okay? I promise. So this is just a preview. 就当做是预习啊，听听看啊。It's just a preview. So consider that we are designing any arbitrary type 1 filter defined over the time region, time range of -n to n, and with this symmetry. Okay, again, back to that for the convenience of discussion. Back to the case of non-causal filter. Let's not worry about causality at first. Suppose that we are designing any arbitrary filter that satisfies the constraint that first, the duration is from -n to n in the time domain. And then secondly, suppose that our filter is evenly symmetric around time 0. Yeah? So evenly symmetric around time 0. Suppose we also have this constraint and 0 elsewhere, 0 elsewhere. That's a constraint. We have this even symmetry constraint. Okay, so then quickly, the frequency response of your impulse, the Fourier transform of the impulse response, that gives you the frequency response, right? So if we denote it as A of omega, you realize that it has this expression. Okay? I like to say A of omega is the good old Fourier transform of the impulse response. That's by definition sum over all n h e minus j omega n, right? We've seen this many times. But if you plug in these constraints, very soon you realize that now it can be expressed in terms of a sum, a constant term, plus 2 times the sum of cosine. N equals to 1 to big N, Hn cosine n times omega. And that's the result of your frequency response. Okay, in terms now it can be expressed because of symmetry. It can be expressed in terms of a sum of cosine terms. So now you must have some kind of a ideal response in your mind. Okay, let's say the ideal response is denoted as H desired. H desired response. Okay, so let's for the sake of generality, your desired response might not even be a low pass. It can be more general. It can be more general. Let's say your desired response consists of two pass bands and a reject band. Okay, something fancy like that. If your desired response is like having 2 separate pass bands, a low pass band and a high pass band, for example, now you have more flexibility. This is your desired response. With that, I'm going to say in here you have a transition place where I don't know. I mean, yeah. Anyway, if your desired response is like that, and now. Now the goal, our formulation goes this way. The goal becomes, in this entire lecture, we're going to focus on the case when our goal is to minimize the maximum approximation error. How do we define the approximation error? Approximation error is defined, of course, by the difference, possibly also weighted, okay? Weighted difference. If we define the approximation error like this. and then consider our design goal to be to minimize the maximum approximation error absolute value. Okay, that's our formulation. So what's going on? So we need a larger space for discussing what's going on. So maybe let's still go back to our good old low-pass filter design as our study case. Okay, it's always easier to begin from something that's simpler. So let's say our desired response consists of a pass band here and a stop band right there. Okay. And somehow it's quite interesting that we allow a, should I say, actually, in the transition that becomes, you'll see in a moment that it becomes a don't care region. We have the pass band and stop band. So in a moment, we'll see an example of defining the error function. Okay, so the one detail to point out is what do we mean the weighting function right here. So let me give you an example. So suppose that now W of omega is 1 for pass band and 2 for stop band, something like that. In between, don't care. Okay? There's a don't care region. Turns out that the transition region is a region that we don't care. Okay? So that's one example. We specify a weight of 1, or the weight may not even be constant. Okay? But I'm just giving you an example when W is piecewise constant. 1 for stop band, 2 for 1 for pass band, 2 for stop band. Okay? There's a weighting function, and our error is defined as weighting function times the difference between our design on the left, subtract ideal response. Okay? Weighted error, so to speak, because this difference definitely is an error, but the error is not weighted. Okay? So now our design goal is to minimize the maximum approximation error. In what range? In omega belong to a collection of intervals where f is defined as the collection of intervals. If this the cutoff frequency is omega p and the beginning is omega s, so now f equals to 0 omega p union with omega s to pi. So that's a frequency range of our interest. We want to somehow minimize the maximum approximation error within within the union of pass band and stop band, within these two intervals in the frequency domain. So that being said, that's why I say in the middle we don't care. It's a bit strange, yeah. So now you see it's a very different formulation, right? We will not talk about convolution in the frequency domain. We will not talk about multiplying a window. There's no notion of a window whatsoever, okay? Very different way of us looking at the problem, with the goal that we want to minimize the maximum approximation error. Or more strictly speaking, we want to find the filter, the argument which minimizes the maximum approximation error within that region by looking at all possible H0, H1, all the way to Hn. So here I'm using a sloppy notation here, okay? So, I mean, if we say H0 is simply H0, H1 is simply H1, just to save space, okay? Just to save space, I'm going to talk about all the samples. We need to design a filter, right? So that is, we need to find out a good impulse response. Okay? So your task becomes to find out what is H0, what is H1, what is H2, all the way, what is Hn. Okay, you need to design this waveform such that you want to find the best filter. You want to find the best filter which minimizes the maximum approximation error in that frequency, in that interval. So 4 levels, okay? Minimizing the maximum approximation in that and finding the filter that satisfies this minimization process. That's a way we are going to formulate filter design, okay, when we come back after the midterm. So the way I read this, by the way, ARG is argument. We're not talking about we want to argue with somebody. Argument is a computer science terminology, right? Do you remember what is an argument? Argument is something you pass to a function. It's called an argument, right? ARG. Something you pass to a function is called an argument. Okay? So we're passing, this is a function. This minimum, no, I'm sorry. Still, this is a function of your choice of filter, okay? Once you choose a filter, you choose all your sample values right there, you can calculate the maximum approximation error given the filter, okay? So now in that regard, your filter is an argument that's passed to this function, okay? And the way we read this expression is that we find a filter, we find the argument which minimizes this maximum approximation error, okay? So that's the way I say it, okay? We find an argument that minimizes the maximum approximation error. So design of the filter becomes an optimization problem. Because minimum maximum error is about optimization. So just to give a preview, turns out that one step further, this is surprising, okay? Now we are going to transform the frequency zone by going to the X domain. If a frequency is omega domain, it turns out that we will use the tool of what we call Chebyshev polynomial to go from frequency omega to X domain using a change of variable, okay? So here, what is X? X is simply cosine omega, okay? So the next step, like when we come back after midterm, you learn that we're going to define a transformation, let's say X equals to cosine omega, to change our frequency axis to the X domain, okay? We'll define that, okay? When we come back after the midterm. So with that change of variable, it turns out that this expression now becomes a polynomial, an nth order polynomial in the X domain. So you'll see that now the entire problem goes to the X domain. It becomes a question of finding the argument, not a polynomial. Finding a polynomial, finding among all possible nth order polynomial that minimizes the maximum approximation error. So it becomes a polynomial approximation problem, surprisingly. And the key step is to realize that any cosine n omega can be written as a polynomial of cosine omega. For example, cosine 2 omega equals to 2 cosine squared minus 1. It's as simple as that. You all learned that in high school. Okay, and they are called the Chebyshev polynomial. And we'll come back to this after the midterm. So you see that optimization problem happens now in the polynomial space, in the high dimensional space of all possible nth order polynomial. How do you choose one to best approximate passband and stopband response? Okay, so now I'll show you one more figure before we leave the classroom for today. So here we'll see that, for example, if you want to design a low-pass filter turns out that you will find a polynomial like that. This is polynomial, right? It looks like a polynomial, right? Which has an equal ripple, plus or minus equal ripple for both the passband and the stopband, and we can have different weight like that. So we are going to penalize any error more in the passband than in the stopband. That's the way we look at it. This W factor, this W right here, can be regarded as a penalty factor. Which controls how much you want to tolerate or you want to not tolerate error in each band of your interest. Yeah. So now just kind of for you to take a look. This looks like a polynomial, right? 看一下有没有像多相似. So now the entire filter design problem is transformed into a polynomial problem. And that's the beauty of this formulation. Okay? Everything now becomes, we talk about polynomials. Okay? So when we come back, we'll touch on, we'll explain more details as well as how to find this polynomial. It's not easy. It hasn't been discovered until, I would say, 1970s. So in terms of math, it's pretty young. Okay, 这不到50年的，可能这50年历史。Pretty relatively new math, an algorithm that has been proposed to find such a polynomial that gives you a best approximation with a passband right here, stopband right here, and when we go back to the omega domain, this gives you this is actually a low-pass filter. Okay, this is a low-pass filter. So that's all I want to say about the preview for optimization-based FIR design. So we will be back tomorrow to talk about follow-up discussions, right? Tomorrow. Okay. Thank you for being here, and have a nice day.